Okay, you guys, where are we at? This one is good. All right, we're gonna walk through 7.2. We're live. Be quiet, Anders. Um, Volume of Revolution Day 1. We've been trying to get this done. We are going to look at volume under a curve if this curve is rotated about an axis. So the first thing you do, Elizabeth, is you think about a disk, which is very similar to a cylinder. What would be the area of, or the volume of one cylinder? Pi r squared gets your surface area times the height. That'd equal our volume. Okay, so that'll cover the circle, area of the circle, and then times the depth of the cylinder. For us, ours are going to be really thin cylinders. So this width or this height or this depth of the cylinder is going to end up being like a dx width to us. Then all we need to do is just stack a bunch of cylinders side by side, which follow the height of the curve, and we can create a three-dimensional object. Except we don't want to have just 3 or 5 cylinders. We want infinite many cylinders, so they're super thin, and that'll give us the sum of all those disks, and we can resort back to integral. So we can say we're going to integrate from some x value, some starting x value, a, and go up to an ending value of b. Those are going to be like our vertical lines where we're integrating between x being a and x being b. We'll take one of these cylinders, pi r squared, times dx. dx representing that depth of the cylinder. Did your hiccup just come over the, was it loud enough, Anders? All right, and then we get area times depth gives us volume. So this is the basic formula. Alrighty, so let's take this problem number 1. Find the volume of a 9-inch long solid cannon shell with a 6-inch diameter at the end. So fairly large. Here's our function, the square root function. Graph it out. Plot points. Max, don't forget your calculator. 0, 0. 1, 0. Or no, 1, 1. Throw in 1, you get out 1. 2, square root of 2. It's kind of poopy. Square root of 3. Kind of poopy. Square root of 4, I like. That's a 2. And they said we have a 9-inch long shell, so we're gonna have our x values ranging between 0 and 9. 9 would be a nice value, so let's throw in 9 and we get out 3. So here was our square root function, yes. Why do I have what? Oh, I don't know. I don't know. Make sure it's less than. It's really emphasized. I don't know why I did that. All right, now we're going to take this segment and reflect it over the x-axis, because what we're going to do is revolve this about the x-axis. And typically you just kind of show a little circular motion for revolution. And if I rotate this point at 4, 2, it's going to rotate down below, or 9, 9, 3 there. And we're going to rotate it around. It'll become 9, negative 3. 4, 2 would become 4, negative 2. 1, 1 becomes 1, negative 1. And 0, 0 still there. So there's our reflection. So as this thing's revolving, the distance of r at any one point is going to be the same distance down below, isn't it? As this arm kind of swings around. Now we can make this look kind of 3D-ish by putting kind of an end to it. What I want us to try and do is draw in one of these cylinders. See if you can imagine. So I'd have one cylinder kind of coming through in here, And there's the front face, there's the center of it. There's some R value to this for the radius of that cylinder. And you can kind of shade that in. There's the thickness of that cylinder. Look decent? Now imagine that we've got infinite number of those disks. We can get our volume by going over to this formula right here. We will integrate from 0 out to 9. So we'll try all the x values that give us all these different cylinders of varying radius. And we want pi. Square root of x really determines the length of our radius, so we get square root x quantity squared times the thickness of our disk dx. This one's not too bad to do by hand. Yes. Why wouldn't the radius be 3? It would be, but only at this outer position, right? Here's where r turns out to be 3, so we'd have some disk out there at the end. But as I travel back to the left, my disks are going to get smaller and eventually really small, right? So what an integral is doing, it's saying let x be 0. Throws in 0, gets out a height of 0. Oh, no volume to that one at all. Then it maybe moves to 0.1 and throws 0.1 in and does calculation, gets its volume. Then it moves to 0.2 and gets the volume and just continues to sum all those different volumes up, but very efficiently, way more efficiently than we can do by hand. All right, so we're going to integrate this and get 0 to 9. We could put the pi out front since it's just a multiplier. And squaring the square root of x would give us just x dx. Now, before we plug any numbers in, you actually have to integrate it. Yeah. So we're going to take the integral of this. Where do I want to put that? That'll be an x squared multiplied by that pi out front. Just adding all kinds of sound effects on yours. Divide by 2. Yes. So x squared divide by 2, and then multiply by that pi from 0 to 9. Throw in 9, and we're going to have 81 halves times pi minus 0. So our answer is 81 pi over 2. And units, what would your units be? Centimeter, or inches cubed, yep. Number 2, set up and evaluate the integral that gives the volume of the solid form by revolving the region about the x-axis. And our function is 4 minus x squared. So what kind of shape's that going to look like? Upside down parabola. It's going to open downwards because of the negative, isn't it? It's going to be at a height of 4, and we're saying we're going to stick with quadrant 1, so we can really just draw the right branch of this. So 4, if we put in 1, we'd have 4 minus 1 is 3, put in 2, and we have 0. So there's our right side of that parabola. That is going to revolve around the x-axis, is what the directions said. So we're revolving about x. If you wanted to try and get a 3D image in your head of this, we could take that segment and reflect it down, couldn't we? So it would be down at -4, so somewhere down in here. There would be the other side of this. So we want to take this and reflect it. What's this going to turn out looking like, you guys? Kind of like a bowl, yeah, if you can imagine a bowl, but only tilted. Like that. It looks like a pie. An apple pie. We got crust on our apple pie. All right. So R. So R is the height from the x-axis up to the curve, right? And if you wanted to, you could try and draw your own little disc in here. It's just fun to draw those. It's not exactly easy, is it? To get a decent drawing, especially on the smart board. Not the easiest. So I have this circular face by the edge, dx edge, and we go into our volume formula. Volume is pi r squared, and our r squared is going to be 4 minus x squared. Yeah, this upper blue bound determines the length of the radius. So we have minus 4x squared, quantity squared, because it's pi r squared, and then multiplied by the thickness, dx. If we have x's in our formula, what must the bounds correspond with? X's as well. So what do we want to integrate between? 0 and the 2, right? 0 and 2. So it said quadrant 1, so we know we've got a vertical block at the y-axis, and then out to 2 where it intercepted the x-axis. Square that out. So if we square this, we're going to have a pi times 16 minus double the product, 8x squared. Square the last thing, the x. Take your integral. Take your integral. I'm looking for my sheet on it, because we end up with some 0 to 2. 16x minus 8x cubed over 3 plus an x to the 5th over 5. And then we'd want to integrate that from 0 to 2. Put 2 in first. This turns out to be, I'm pretty sure the number is 256 pi, common denominator of 15. I'm pretty sure that was the answer, guys. Just to save us a little time. All right, goodbye, apple pie. You know what, let's clear all that. And this is our last example. Tomorrow we'll work with revolving around the y-axis. Today it's just x-axis. Hey, we're doing well. We're only at 12 minutes. So it says, find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the x-axis. How would you graph this? What shape is it? Parabola opening up. Do you know how low it goes? 5. If I plugged in 0 for x, it looks like it'll be at -5 or +5, doesn't it? If we plug in 0, we get out 5. But that's probably not the vertex, is it? No. Do you remember how to do this in advanced algebra? Complete the square. You got it. Do you remember how to complete the square? We got time. Let's do it, because that's a good skill to go back over. They don't take very long. Right? You just got to fill in the box. Crush this. Middle term divided by what? 2, and then you square it. That completes the square for you. So we're going to take -4 divided by 2 and square that, and that's going to give us -2. Quantity squared gives us 4. 4 is the magic number. Now, what did that do for us? Well, it creates or else I just ignored. They're talking about 3 being a magic number. X minus 2 quantity squared plus 1. Because what we generate here is a perfect square binomial, isn't it? Yeah. So when I wrote my equation, I have y over here, don't I? And so on the right side of my equation, I have +4 that I introduced, right? I introduced this. To keep things at a 0, I'm going to subtract it off this side. So then 4 minus 4 ends up being neutral. That makes sense? I bet when you guys did it in advanced algebra, did you put it on the other side? So you were always, if you added on one side, you added to the other side. Yep. So instead, I'm just keeping everything on the right side. It's just a little bit more efficient. That gives us h comma k, doesn't it? What's hk? The vertex of the parabola. Does this come back to you now? And hk is, the normal format was h minus k quantity squared, or x minus h quantity squared plus k. So our vertex is at 2, 1. 2, 1 is the bottom of this parabola, and we had already that marking. Otherwise, you can plot points, right? Which we probably want to do anyway. But it's just a good review to go back over, complete the square. Let's throw in 1. If we throw in 1, we get 1 minus 4 is negative 3. This will be a 2. Symmetry, then, if this is my vertex, now I can use symmetry to finish mapping this out. That'll give us this shape. There's our parabola. Let's get rid of this work. Also, we have an x equals 1, so vertical line at 1. And we have a vertical line at x equals 4. And y equals 0, which is our x-axis. Does that define a region for you? Yes. We have a nice region. Whoopsie. We have a nice region here defined. That's what we want to revolve, isn't it? I'm going to get rid of this extra stuff right along there. Now, oops. We're going to revolve this, reflect this over the x-axis. So just imagine this flipping over, and I'm going to flip mine. About there. And you can see, here's the shape, the 3D shape coming out of that as it revolves. So you'd have, you know, kind of a, looks like a speaker or something to me. This side we wouldn't see maybe. Yeah. So what is the radius that's revolving? Well, anything from the top curve to the bottom curve, right? That defines the length of my radius. Sort of like when we did area, it's still top minus bottom gets me the length of this segment. Instead of just being a rectangle like it was when we were doing area, we're now revolving it so it becomes a cylinder effect or a disc in here. So there's the thickness of my disc, and many of them. So we get volume equals an integral from where to where? 1 to 4 pi r squared. In this case, r is determined by top function x squared minus 4x plus 5. Bottom function is 0, so I don't need to write it, squared dx. No, because pretty soon we're going to take our function and maybe move it up and have even a region down below it, and then we can define this region and revolve it. That'll give us a hole in the center. So then it'll become r will be, we'll have one r there and a little r here. So we'll get an r squared, I'll go big R squared and little r squared, so that we can subtract out the inner volume. So I have large volume minus inner volume. So it will shift. We also can shift, we can also shift the axis of rotation. So this is by far the easiest one that we do, and then we'll start moving things around. Tomorrow we'll go about y's, and then everything's got to be shifted into y, x equal y equations. So, calculator this. All right? Grab your calculator and see if you can get a value out of this. So load it up. You could graph it. It looks like what we had. And the only place you can get your integral work is from your home screen. So go to your home screen and set up your integral. For some reason, I think my whole screen just cleared. What was it, from 1 to 4? And mine is sitting in y2. So, hey, the easiest thing to forget is your pi sign. Get pi in there. So we have pi. Uh-oh, I got h. All right. Pi, and then it's r squared. For me, I have things sitting in y sub 2. So I have to go to my y sub 2 equation. And that needs to be squared. And then dx. Did you get that? 49.008 would be accepted, or 49.009 would be accepted. Or you could give 3 decimals, 5 decimals, or 4 decimals, 5 decimals, however many you want for the AP exam. All right, that covers what we need to do today, you guys. And that should take you to this homework page. Just do the top 3 functions, okay? Find the volume of the top 3, and we'll see you tomorrow.